December 7, 1941. The Japanese attack on Pearl Harbor doesn't just sink battleships, it severs something far more critical to America's ability to fight a modern war: rubber. Specifically, the supply lines that bring it from Southeast Asian plantations to American factories. Within weeks, Japan controls 97% of the world's natural rubber supply. Every tire, every gasket, every hose, every piece of flexible machinery in the American military depends on a material that's now in enemy hands. The numbers are brutal. America needs roughly 840,000 tons of rubber annually just to maintain its existing civilian economy. Military production for a two-front war will demand at least double that. On December 7, 1941, American stockpiles hold exactly 630,000 tons of crude rubber. At current consumption rates, that's a 14-month supply. After that, the American war machine quite literally stops moving. German military planners are watching these calculations with satisfaction. Their own synthetic rubber program, developed throughout the 1930s under autarky policies, means they're not dependent on overseas supply lines. German chemists at IG Farben have been producing Buna rubber since 1936, roughly 30,000 tons annually by 1941. It's not perfect. It's more expensive than natural rubber and has different performance characteristics, but it exists, and Germany has it. America doesn't. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The German assumption, shared by Japan, is straightforward. America's industrial advantage means nothing if its tanks, trucks, and aircraft can't move. Cut off the rubber supply, and you've effectively grounded the largest manufacturing economy on Earth. This isn't speculation. This is chemistry and logistics colliding with strategic reality. Every Sherman tank requires over half a ton of rubber components. A single B-17 bomber uses more than 800 pounds. A Liberty ship needs 18 tons. Without rubber, none of these machines function. Washington understands the crisis immediately. On January 7, 1942, exactly 1 month after Pearl Harbor, President Roosevelt establishes the Rubber Reserve Company as a subsidiary of the Reconstruction Finance Corporation. The mandate is simple and terrifying. Create a synthetic rubber industry from essentially nothing, and do it fast enough to prevent industrial collapse. The target is 650,000 tons of synthetic rubber production annually by 1944. For context, American synthetic rubber production in 1941 totaled just 8,300 tons, all experimental. The problem isn't that synthetic rubber is impossible. German success proves otherwise. The problem is that America has no infrastructure, limited chemical engineering expertise in this specific field, and patents for the best processes are held by German companies that obviously aren't sharing. American chemists need to reverse engineer, innovate, and scale up industrial production simultaneously, while fighting a war on two fronts with a ticking clock measured in months, not years. The chemistry of rubber, natural or synthetic, comes down to polymer chains. Natural rubber is polyisoprene, long molecules of repeating isoprene units that give the material its characteristic elasticity. The rubber tree, Hevea brasiliensis, produces latex sap containing these polymers in a convenient liquid form. You tap the tree, collect the latex, coagulate it, and process it into usable rubber. This method has worked for centuries, refined to industrial scale by British and Dutch plantations across Southeast Asia. It's efficient, relatively cheap, and completely dependent on geography and climate that America doesn't control. Synthetic rubber means building those polymer chains artificially in chemical reactors. The Germans focused on butadiene-based polymers, specifically combining butadiene with styrene to create Buna S, or butadiene with acrylonitrile for Buna N. American chemists, racing to catch up, initially didn't know which approach would work best. They didn't have time for methodical research. They needed to pick a direction and scale it up immediately, knowing that wrong choices now would cause catastrophic failures later. The Rubber Reserve Company makes a calculated bet. Focus on styrene-butadiene rubber, or SBR, similar to German Buna S, but with modifications learned from limited pre-war research. This requires building two entirely new chemical industries simultaneously. First, styrene production from petroleum. Second, butadiene production, also from petroleum. Then, facilities to polymerize these chemicals together. None of this infrastructure exists in 1942 at anything approaching the necessary scale. Styrene production becomes the first engineering nightmare. The molecule is simple enough, a benzene ring with an ethylene group attached, but making it in 100,000-ton quantities requires enormous petroleum refineries with specialized catalytic processes. Standard Oil of New Jersey and Dow Chemical have some pilot plants, but nothing remotely sufficient. The government contracts for 15 massive styrene plants to be built across the country, from Texas to New Jersey. Each plant needs custom-designed reactors, distillation columns, 5 stories tall, and safety systems because styrene is both toxic and explosive. Construction starts in February 1942. Engineers are literally drawing blueprints while contractors are pouring foundations. The Dow Chemical facility in Velasco, Texas, begins operation in November 1942, just 9 months from groundbreaking to production. By any measure, this is insane. A chemical plant of this complexity typically requires 18 to 24 months of planning before construction even starts, but there's no time. Every month of delay means thousands more tons of irreplaceable rubber consumed from dwindling stockpiles. Butadiene production presents different challenges. The molecule can be synthesized from petroleum or from alcohol derived from grain. The petroleum route is more efficient but requires different refinery configurations. The alcohol route is slower and more expensive, but uses existing grain surpluses and distillation infrastructure. The Rubber Reserve Company funds both approaches simultaneously, betting that redundancy matters more than efficiency when failure means losing the war. The first butadiene plant, built by Shell Oil in Torrance, California, goes online in April 1942, producing roughly 3,000 tons per month. By December 1942, 8 additional plants are operational. But here's where American industrial scale shows its power. Each new plant incorporates lessons learned from the previous ones, creating an acceleration curve that German planners never anticipated. By mid-1943, American butadiene production exceeds German production by a factor of 5, despite starting nearly a decade later. Polymerization facilities, where styrene and butadiene combine to form synthetic rubber, require yet another wave of construction. These plants feature massive steel reactors, where the chemical magic happens under carefully controlled temperature and pressure. The process uses emulsion polymerization, mixing the monomers with water, soap, and chemical initiators, then heating the mixture to roughly 50 degrees Celsius for 12 to 18 hours. The result is a latex emulsion similar to natural rubber sap, which then gets coagulated, washed, dried, and baled. The U.S. government contracts for 51 synthetic rubber plants between 1942 and 1944. The largest, operated by Firestone in Akron, Ohio, and by Goodyear in Houston, Texas, can each produce over 30,000 tons annually. These aren't just scaled-up laboratory experiments. These are purpose-built industrial complexes covering hundreds of acres, employing thousands of workers, consuming trainloads of raw materials daily. By June 1943, just 18 months after Pearl Harbor, American synthetic rubber production hits 30,000 tons per month. This is the inflection point where crisis transforms into advantage. The stockpiles of natural rubber are nearly exhausted, dropping below 300,000 tons, but synthetic production is ramping up fast enough to cover the gap. More critically, the chemical engineers have figured out something the Germans missed. SBR can be formulated with different properties by adjusting the styrene to butadiene ratio. High styrene content, around 35 to 40%, creates rubber with excellent abrasion resistance, perfect for tire treads. Lower styrene content produces rubber with better low-temperature flexibility, ideal for aircraft components and cold weather applications. This versatility means American industry can tailor synthetic rubber to specific military needs, rather than forcing compromise formulations. The military testing begins in earnest throughout 1943. The Aberdeen Proving Ground in Maryland runs tire durability tests, mounting experimental SBR tires on trucks and driving them through obstacle courses designed to simulate combat conditions. Early results are mixed. The synthetic rubber tires wear differently than natural rubber, showing more resistance to cuts and punctures, but less resistance to heat buildup during high-speed operation. Engineers at the Goodyear Technical Center discover that adding carbon black, a fine powder of nearly pure carbon, to the rubber compound dramatically improves durability. The carbon black acts as reinforcement, preventing crack propagation and reducing wear rates. By mid-1943, SBR tires with optimized carbon black content are matching or exceeding natural rubber performance in most applications. Aircraft components present tougher challenges. The rubber hoses, seals, and gaskets in aircraft fuel systems must resist petroleum products while maintaining flexibility at high altitude, where temperatures drop to -40 degrees Celsius. Natural rubber excels at this. Early SBR formulations fail catastrophically, becoming brittle and cracking at low temperatures. Chemical engineers respond by developing specialized variants, incorporating different monomers like acrylonitrile to improve oil resistance and cold flexibility. By November 1943, American factories are producing GRA, government rubber acrylonitrile, specifically for aircraft applications. It costs nearly twice as much as standard SBR, but it works. B-17 seconds and B-24 seconds flying over Germany at 25,000 feet aren't experiencing fuel system failures anymore. The problem is solved through brute force chemistry and unlimited funding. Tank components require yet another specialized formulation. The tracks, road wheels, and suspension systems of M4 Sherman tanks operate in conditions that destroy ordinary rubber within weeks. Mud, sand, extreme temperatures, and constant mechanical stress. Ordnance Department testing at Fort Knox shows that natural rubber track pads last roughly 400 miles before needing replacement. Early synthetic versions fail at 200 miles. Engineers at the Firestone Development Laboratory tackle this by creating a synthetic rubber with higher butadiene content and specialized cross-linking agents that increase tensile strength. The result, designated GRT for Government Rubber Tank, shows trackpad life exceeding 500 miles by early 1944. Sherman tanks rolling off Detroit production lines are now equipped with synthetic rubber components superior to the natural rubber they replaced. The strategic implications become clear by mid-1944. American synthetic rubber production hits 70,000 tons per month, exceeding total military requirements even with the D-Day invasion consuming enormous quantities. The surplus allows stockpiling for future operations and provides cushion against production disruptions. More critically, the chemical engineering expertise developed during this crash program gives America permanent industrial advantages that will extend decades beyond the war. German intelligence reports from this period, captured after the war, reveal genuine shock at American achievements. Abwehr assessments from July 1944 note that American synthetic rubber production has surpassed German production by approximately 6-1, despite Germany's decade head start. The reports specifically mention American success in creating specialized variants for different applications, something German industry struggled to achieve even with more mature technology. The real test comes not in laboratories or proving grounds, but on the beaches of Normandy and in the jungles of the Pacific. June 6, 1944. Operation Overlord puts American synthetic rubber to the ultimate stress test. Every truck, jeep, and tracked vehicle rolling off landing craft at Omaha and Utah beaches rides on tires that didn't exist 3 years earlier. The logistics are staggering. The invasion force requires approximately 450,000 vehicle tires, plus countless gaskets, hoses, belts, and seals. If synthetic rubber fails at scale under combat conditions, the entire Allied advance into France stalls before it begins. The initial reports from Normandy are mixed but revealing. Quartermaster Corps officers note that synthetic rubber tires perform differently than soldiers expect based on pre-war experience with natural rubber. The sidewalls are stiffer, requiring slightly higher inflation pressures. The tread compounds wear more evenly but show different patterns of deterioration. Drivers report that vehicles handle slightly differently, particularly in wet conditions where synthetic rubber provides marginally less grip on pavement. But here's what matters. The tires don't fail. Trucks hauling ammunition from the beaches to forward positions cover hundreds of miles across cratered roads, through mud, over temporary bridges made of steel planking. The synthetic rubber holds. Jeeps carrying wounded soldiers back to field hospitals run 20 hours per day, their tires flexing over debris and shell fragments. They keep moving. By July 1944, after a month of the most intensive vehicle operations in military history, failure rates for synthetic rubber tires are running at approximately 3% compared to roughly 2.5% for natural rubber in comparable service. Statistically insignificant. The breakthrough comes in late July during Operation Cobra, the American breakout from the Normandy hedgerows. General Patton's Third Army begins its race across France, covering distances that strain logistics to the breaking point. Trucks in some units drive over 200 miles in single days, often on roads damaged by bombing or torn up by tracked vehicles. The Quartermaster Corps tracks tire wear obsessively, knowing that if synthetic rubber can't sustain this pace, the entire offensive collapses. August 19th, 44 data shows something unexpected. Synthetic rubber tires are actually outlasting natural rubber in high-speed, long-distance operations. The higher heat resistance of SBR means less internal breakdown during sustained highway driving. Convoys running supplies from Cherbourg to forward units near Paris are getting 12 to 15,000 miles from tire sets, compared to 8 to 10,000 miles from equivalent natural rubber. Tires in World War I service data. Field modifications tell their own story. Maintenance units start requesting specifically synthetic rubber components for certain applications. Tank crews prefer the synthetic rubber track pads because they last longer between replacements, reducing downtime. Artillery units favor synthetic rubber tires on towed guns because the stiffer sidewalls handle rough terrain better without pinching. Within 6 months of D-Day, synthetic rubber isn't just adequate. In many applications, it's preferred. The Pacific theater presents entirely different challenges. Heat and humidity that make Europe look mild, terrain that varies from volcanic ash to coral sand to knee-deep mud, and supply lines stretched across thousands of miles of ocean. The 1st Marine Division landing on Peleliu in September 1944 provides brutal testing conditions. Temperatures exceed 110 degrees Fahrenheit. Coral limestone shreds conventional tire treads, and resupply is uncertain at best. Combat reports from Peleliu note that vehicle tires, all synthetic rubber by late 1944, are holding up better than expected. The coral is abrasive enough to wear through tread in a fraction of normal service life, but the tire casings themselves resist cutting and tearing. Vehicles abandoned with flat tires can often be recovered and fitted with new tubes, whereas natural rubber tires in similar conditions would have deteriorated completely. The synthetic rubber's resistance to ozone and UV degradation, properties that seemed academic in laboratory testing, prove critical in tropical sunlight. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The Philippines campaign, starting in October 1944, scales up Pacific operations to match European intensity. General MacArthur's return to the islands involves moving entire armies across archipelagos with minimal port infrastructure. Synthetic rubber becomes the invisible enabler of mobility. Landing craft carry trucks and jeeps that immediately drive inland on whatever roads exist, often just packed earth or gravel. The vehicles need to function immediately, without time for maintenance or adjustment. Quartermaster data from Leyte shows tire failure rates of approximately 4% across all vehicle types, slightly higher than Europe, but well within acceptable ranges given the extreme conditions. More significantly, Vehicles can operate for weeks without access to replacement tires, because the synthetic rubber resists the environmental degradation that would have destroyed natural rubber in similar circumstances. Humidity that would rot natural rubber from the inside out barely affects synthetic compounds. The Okinawa invasion in April 1945 provides the final Pacific test case. The island's terrain combines everything difficult about Pacific operations: volcanic soil that's abrasive, monsoon rains that create mud, and temperatures that fluctuate between freezing nights and sweltering days. Over 500,000 vehicle tires support the operation, every single one synthetic rubber. The campaign lasts 82 days of sustained combat operations. Post-battle analysis shows that tire failures accounted for less than 2% of vehicle downtime, a remarkably low figure given the operational tempo. More telling, recovery teams find abandoned vehicles with tires still inflated and functional after weeks exposed to weather. The synthetic rubber simply isn't breaking down the way natural rubber would. This durability means vehicles can be salvaged and returned to service, rather than stripped for parts. Meanwhile, German forces are experiencing the opposite trajectory. By late 1944, German synthetic rubber production is collapsing under Allied bombing. The IG Farben plants at Ludwigshafen and Leverkusen, primary sources of Buna rubber, are hit repeatedly by 8th Air Force raids. Production drops from 35,000 tons monthly in January 1944 to less than 10,000 tons by September. The Wehrmacht is cannibalizing tires from captured vehicles and manufacturing ersatz rubber from whatever materials are available, including reclaimed rubber mixed with sawdust and tar. German military logistics reports from autumn 1944, captured after the war, reveal desperation. Units are ordered to remove tires from all non-essential vehicles and pool them for combat operations. Trucks are running on wooden wheels wrapped with steel straps, a technology that hadn't been used since World War I. Tanks are operating with damaged track pads that should have been replaced months earlier, accelerating mechanical failures across armoured formations. The contrast becomes stark during the Battle of the Bulge in December 1944. German forces launch their final major offensive through the Ardennes, and logistical analysis shows that rubber shortages directly limit their operational reach. Panzer divisions can't maintain sustained advances because their vehicles are breaking down from worn components that can't be replaced. Half-tracks are abandoned when track pads disintegrate. Trucks hauling ammunition and fuel are sidelined with tire failures. American forces, despite being caught by surprise, recover partially because their logistics hold up. Vehicles can be pushed hard without catastrophic failure rates. The synthetic rubber components simply work. Patton's Third Army pivots north and covers over 100 miles in 48 hours, a movement impossible without reliable tires on thousands of trucks. The Battle of the Bulge becomes, among other things, a demonstration of logistics determining tactical outcomes. Intelligence assessments from interrogated German officers reveal their perspective. Multiple sources independently note shock at American vehicle reliability under extreme conditions. A Waffen-SS logistics officer, captured in January 1945, specifically mentions American tires, stating that captured vehicles showed minimal wear despite obvious heavy use. German intelligence had assumed American synthetic rubber was inferior to their own Buna production, based on pre-war assessments. By late 1944, field evidence proved that assumption catastrophically wrong. The strategic implications extend beyond immediate battlefield performance. American synthetic rubber production in 1944 reaches 895,000 tons, exceeding the total pre-war consumption of natural rubber. This production continues in 1945, reaching over 920,000 tons despite the war in Europe ending in May. The Pacific War's continuation through August means sustained demand, but production capacity now exceeds requirements by comfortable margins. This overcapacity proves critical during the final Pacific campaigns. The planned invasion of Japan, Operation Downfall, requires stockpiling resources on a scale that dwarfs previous operations. Planners estimate needing over 2 million vehicle tires for the invasion force, plus enormous quantities of other rubber products. The synthetic rubber industry can meet these demands without straining. The invasion never happens, made unnecessary by atomic weapons and Soviet entry into the war, but the industrial capacity stands ready. The cost of building America's synthetic rubber industry was approximately $700 million between 1942 and 1945, equivalent to roughly $11 billion in 2025 dollars. This represents one of the largest single industrial programs of the war, comparable to the Manhattan Project in scale, if not in technological complexity. The return on investment becomes clear when you calculate the alternative. Without synthetic rubber, American military operations would have been constrained by natural rubber availability, limited to perhaps 40% of actual wartime production levels. This means fewer vehicles, slower advances, longer campaigns, and substantially higher casualties. Conservative estimates suggest the war in Europe might have extended into 1946 and the Pacific War into 1947 or beyond. The synthetic rubber program didn't just support the war effort, it determined the war's timeline. The chemical engineering expertise developed during this crash program had immediate post-war applications. The same facilities producing SBR for military use transitioned seamlessly to civilian production. By 1946, synthetic rubber was being manufactured for civilian automobiles, industrial applications, and consumer goods. American tire companies discovered that synthetic rubber's consistency and predictable properties actually made it superior to natural rubber for many applications. Natural rubber varies in quality depending on plantation location, harvest timing, and processing methods. Synthetic rubber comes out of the reactor with identical properties batch after batch. This consistency allows tire manufacturers to optimize designs more precisely, creating products with better performance and longer life. By the early 1950s, roughly half of all rubber used in American tires was synthetic, chosen for technical reasons rather than supply constraints. The technology spread internationally through post-war reconstruction programs. European nations, rebuilding their industrial bases, adopted American synthetic rubber processes rather than relying solely on colonial natural rubber supplies. Japan, its Southeast Asian conquests lost, built synthetic rubber plants using American technology transferred through occupation authorities. By 1960, global synthetic rubber production exceeded natural rubber production for the first time in history. The irony is rich. Germany's autarky policies of the 1930s, driven by fear of blockade, led them to develop synthetic rubber technology. They assumed this gave them strategic advantage over resource-dependent democracies. Instead, America's industrial scale and systematic approach to chemical engineering allowed it to not just catch up, but surpass German production within 3 years of starting essentially from zero. The head start meant nothing when confronted with American industrial capacity unleashed by necessity. The German chemical industry's pre-war dominance in synthetic materials evaporated because they couldn't scale production fast enough under wartime conditions. American industry, less sophisticated initially, proved more adaptable and vastly more productive. This pattern repeated across multiple technologies during World War II, but synthetic rubber might be the clearest example. The side with better chemistry lost to the side with better engineering and unlimited resources. Modern tire technology traces directly back to wartime synthetic rubber development. Current passenger car tires use styrene-butadiene rubber formulations that would be recognizable to chemists working at Goodyear in 1943, though with refinements from 8 decades of additional research. High-performance tires incorporate different synthetic polymers, but the fundamental concept remains: build polymer chains with predictable properties, rather than depending on natural variation. The strategic lesson transcends rubber specifically. World War II demonstrated repeatedly that industrial capacity matters more than initial technological advantage. Germany had better tanks, better aircraft designs, and more advanced chemistry at the war's start. None of it mattered when American industry could produce adequate alternatives in overwhelming quantities. The Sherman tank wasn't as good as a Panther tank one-on-one, but America built 50,000 Shermans. Germany built 6,000 Panthers. Synthetic rubber fits this pattern perfectly. Buna rubber was technically sophisticated, the product of decade-long development by world-class chemists. SBR was more crude, developed in frantic haste by engineers who were making it up as they went. But America produced 10 times more of it, in facilities built from scratch in a fraction of the time German planners thought possible. Quantity has a quality all its own, and America's synthetic rubber program embodied that principle absolutely. The environmental and economic impacts continue today. Natural rubber cultivation requires specific tropical conditions and displaces rainforest agriculture. Synthetic rubber production uses petroleum feedstocks and generates chemical waste, but it's geographically unconstrained and scalable to demand. Modern production splits roughly 50-50 between natural and synthetic, with synthetic dominating applications requiring consistent performance. The wartime crash program created an entire industry that now produces over 15 million tons annually worldwide. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.